So welcome everybody to In Conversation With. Today we'll be talking with Mike Crommie of the Material Sciences Division and the Physics Department at UC Berkeley. We'll start as always with his research interests taken from his website, and I quote, "Our research interests lie in exploring the local electronic, magnetic, and mechanical properties of atomic and molecular structures at surfaces. We're interested in studying how local interactions between atomic scale structures affect their microscopic behavior, and how quantum mechanical effects might influence nanodevice behavior in very small structures. Our main experimental tool is scanning tunneling microscopy, which we use in combination with other experimental tools to both fabricate atomic scale structure and probe them spectroscopically. Please join me in welcoming to In Conversation With Dr. Mike Crommie." All right, so let's start at the beginning. Where were you born?
Beverly, Massachusetts.
When and why did your family move to Ann Arbor, Michigan?
Because my father was in the defense industry and he was taking classes there at the University of Michigan. What was he learning? He was, I think he was learning how to solve differential equations.
So you lived a very nomadic life when you were young. From Ann Arbor, your family moved to Alabama.
Yeah.
While in Alabama, your parents got divorced.
Right.
And then you, your mom, and your siblings moved to California.
Right.
You lived in Long Beach, then moved to Fresno,
Right.
then to West LA, and Redondo Beach.
Yeah. And then
Finally, when you were in 7th grade, you moved to Santa Monica, where you would stay until graduate school.
Yes.
Now, you once said that you loved Santa Monica. What did you love about it?
Well, growing up there in the 70s was a lot of fun because there was a beach, and so there was always something to do. We could go to the beach.
You weren't a surfer, but you surfed.
Yeah, I surfed. I was the world's worst surfer, but I did a lot of body surfing and hung out at the beach with my friends, played volleyball, and just go and splash around and other things.
So you are one of 4 children. What's
Yeah.
the birth order? Where are you?
I have my oldest brother, and then my older sister, and then me, and then my younger sister, all about two or 3 years apart.
And what did your parents do?
My dad early on was a rocket scientist. He was helping design, actually an aerospace engineer. I'm not sure what a rocket scientist actually is, but he was an aerospace engineer, which I guess is the closest thing. He was working on designing missiles, and he worked on the Apollo space program for a little bit back when I was young. During that time, my mother was a housewife, but then after they got divorced in the 60s and my father moved on, he went back to school, became an economist, and my mother became a social worker, and then a psychotherapist, which she still is right now. She's practicing psychotherapist.
I may get her number from you. So when you were, I asked you once who you admired when you were young. And some people want to be a cowboy or whatever. And at first you said that you admired the cool guys in high school because they got all the girls, and you wouldn't have minded getting all the girls. But then you thought about it, and you changed your answer to writers. What kind of writers did you admire?
I was reading a lot of science fiction and fantasy at the time. So I guess writers like Arthur C. Clarke, Robert Heinlein, J.R.R. Tolkien, those types, those old school fantasy and science fiction.
And also a lot of kids when they're young, when they grow up, they want to be firemen. But you thought you wanted to build rocket ships. Did this idea come from your dad or from the books you were reading? Where did you get this idea that engineering rocket ships would be cool?
Oh, I don't know, but it had to be from my dad, I guess. That's what he was doing. So it must have been influenced from him. It seemed cool. I just knew that I always wanted to do something really fun and interesting, and that seemed fun and interesting at the time.
So you went to Santa Monica High School,
Yeah.
but you weren't a joiner. You played basketball, you played football, but you didn't join the teams. You weren't in any clubs. You had friends, but you moved between different social groups without really joining any particular group. But there was something going on in Santa Monica at that time that I think is interesting. Can you tell us a little bit about Dogtown?
Yeah. At Santa Monica in the 70s, that was when the whole skateboarding craze was born. It originated in Santa Monica. During that time, that was when there was sort of a select group of kids about my age who were really wild and daring and started taking the skateboards and seeing what they could do with them, and they were starting to skate in empty pools and go off jumps and starting to figure out all the things you can do with skateboards, and that was kind of the beginning of the whole skateboard craze.
And that was going on around you. You saw that?
Yeah, it was happening around me, but I wasn't really, I was more watching it, I wasn't really part of it.
But you were, I heard that you were beat up by a soon-to-be famous skateboarder when you were in high school.
That was the closest I came to joining it.
But that's very cool, because I was beat up in high school too, but by a nobody. So at high school, what AP classes did you take, and how did you do on the exams?
I took AP History and AP Calculus, and but I didn't take the exams because I forgot to sign up in time.
Remember that, it's going to come back later in the story.
Don't let them know. It's embarrassing.
While you were in high school, you took a course at UCLA. What did you take, and how did that come about?
Some calculus course. I'm trying to remember how that came about. They just, geez, I barely remember so long ago, but there was an opportunity to take math, while in high school, to take math courses at UCLA. So I thought that'd be kind of cool, and so I did it. So I would ride my bicycle from Samo High up Wilshire to UCLA.
So when you were a senior in high school, you had known for a while that you wanted to go to college. So how many colleges did you apply to?
None. I didn't apply to college. I just never got around to it.
So you didn't apply to college, but you did go. You ended up going to UCLA. How did you get into UCLA without applying?
Well, because I was taking that class, and so someone said that I could just take other classes, and so I just started signing up for other classes.
So you just showed up?
Yeah. You could do that back then.
So compared to Santa Monica High, how did going to UCLA change your commute?
Well, I just hung a right on Wilshire instead of hanging a left on Pico.
And you rode your bike?
I rode my bike, yeah.
So even though you enjoyed English and history in addition to science and math in high school, by the time you got to college, you knew that you wanted to focus on science. But you didn't exactly know what kind of science. When you first got to UCLA, what did you think you wanted to do?
Well, I was interested in the idea of being an engineer, an aerospace engineer, or then I was starting to move and think about becoming an electrical engineer, because that seemed pretty interesting. But then I started looking seriously into what it actually meant to be in those fields, and I realized that when I started learning more about them, I realized that they didn't really suit me, that I didn't, wasn't quite as interested in those areas as I thought I was.
Mm-hmm. But you did decide on a double major.
Yeah, well, I knew I wanted to be in some technical field, and so as I was gearing up to be an engineer, I was taking math and physics and starting to look at the engineering courses, and I realized I didn't want to take the engineering courses, and I just kept taking the math and physics courses, which I liked, and so I just kept taking them more and more.
And you thought you would be a double major in math and physics?
Yeah, I didn't know what I would be, actually, but I liked math and physics, so I just kept taking them. I was a double major in math and physics.
Mm-hmm. But you didn't end up graduating with a double major. You were one course shy of completing your math degree. What happened?
Well, I realized that I hate math. But I had to take a lot of it to figure that out.
You must have liked something about math to get that far.
Well, I did, yeah. I mean, I was pretty good at it, and I thought I liked it. But then I discovered that I actually liked it when I was applying it to physics problems.
Okay. So the beauty and structure of numbers wasn't exactly your...
Oh no, I realized I really don't appreciate that at all. But I had to get high up to realize it.
So while you were at UCLA, you worked for George Brunner and his group.
Yeah.
How did you meet Brunner?
Brunner taught a solid-state physics course that I took at UCLA, and that was what really turned me on to solid-state physics. I really liked the idea of how he really showed how quantum mechanics can be applied to determine the properties of everyday materials, which was for me kind of a revelation, and I thought that was really cool. And that's what really got me into solid-state physics.
And at that time, Brunner's group was studying charge density wave materials.
Yeah.
What was your job in his group?
Well, I went to him and I wanted to do research, and so he gave me this problem. He wanted me to theoretically explain how charge density waves polarize in the presence of an electrical field, because the charge density wave has different segments to it, and as you apply an electric field, there's all these nonlinear interactions, and it can kind of squish over to one side in a certain way in response to an electric field. And so he asked me to model that theoretically and calculate the IV curves that they were measuring experimentally. So I was this little undergraduate who didn't know anything, and he gave me this problem.
Did you ever think maybe he just didn't want you touching the equipment?
In retrospect, now that I hire undergrads, I realize what he was doing. Just send him off and see what he can do. But it was fun. It was good. I actually, came up with something and modeled it, and we wrote a paper. We ended up writing a paper on it.
Now, who is Laszlo Mehi, and what role did he play in your undergraduate career?
Well, he was the postdoc for George Brunner at that time. He's now professor at Stony Brook, and he was a person who I really interacted with, Laszlo Mehi. And so he's a great guy. He's really helped me out a lot. He was a person who, was showing me how to do stuff. But it was all theory. I didn't do any experiments.
But you finished your degree in physics. You got your BS in physics. When did you know that you wanted to go to graduate school?
Well, I think that's something that I knew kind of all along. Well, in the sense, I was one of those people who, you know how it is, if you don't know what you want to do, you just keep going to school. You just keep doing what it is you're doing. And I liked going to school, and I liked, and I was good at it, and I liked it, so I just kept doing it.
But unlike applying to college, you took applying to graduate school very, very seriously. And you knew that you wanted to go to a good school. And you, in fact, did get accepted into quite a number of top schools. Tell us about MIT, Harvard, and Berkeley.
Well, those are the ones I liked the most. And MIT, but when I visited MIT, I liked it. There seemed to have the most women there at MIT. The female, the ratio was best there, but the campus was not so attractive to me. And Harvard was very cool with Harvard Square and the trees and the red stone buildings, and that clubby atmosphere was kind of appealing. But Berkeley also, was very cool. I was from Southern California, so coming to Northern California and seeing Berkeley and Telegraph Avenue in San Francisco, that was all very exciting. And the campus was so beautiful with the redwood trees and a little stream through it.
So it came down to Harvard and Berkeley.
Yeah.
And there was an acceptance deadline that you took seriously, and you knew that you had to make a call before the cutoff time. How easy was it for you to make that decision between Harvard and Berkeley, and what did you ultimately choose?
Well, now that I've been on the admissions committee, I realize that deadline isn't so, important. But at the time, I thought it was very important.
You're telling us all these secrets.
But it was a very hard decision for me to make. There was like a time cutoff, and I was just sitting there next to the telephone trying to decide, and I couldn't decide which school to go to right up until the very minute. And so right at the very last moment, I just made the decision to go to Berkeley at literally the last moment.
And you never regretted it?
No.
So since you quit the math degree, that was extending your undergraduate stint at UCLA, you ended up graduating in December, which gave you 8 or 9 months between the time you graduated and the time that you started graduate school. What did you do with that time?
Well, that was a really good experience, a good time, because I went out and got a job. And at that time, when was that? That was like 1984, or the end of 1984, 1985, and there was a lot of money in the defense industry. That was the height of Star Wars. Remember Star Wars? And so there's a lot of money in Southern California for these defense companies like Hughes, TRW, the Aerospace Corporation. All those places were hiring, McDonnell Douglas, and so I ended up taking a job at TRW, and that was a really cool place to work because they had a research group which was doing it was really neat. They were making squid circuits and solar cells, actually, and they were making gallium arsenide lasers, solar cells, and various squid circuits. What are you looking at? Oh. and so my job there, I got to make solar cells. So I was making solar cells there for them, although I didn't really know too much what I was doing. I was doing CAD layout for lithographically designed solar cells, but I was also doing numerical simulations of Josephson junction circuits. They were trying to make analog to digital converters using squids in some various configurations, and so they wanted me to numerically simulate how these circuits might behave if they were to build them,
And you said you did that modeling old school. What do you mean by that?
Oh, well, just,
like you actually did it yourself?
Yeah, like solving all the coupled nonlinear differential equations, iterating in time using Runge-Kutta,
But nowadays they're packaged.
Yeah, now
programs.
I think it's the Josephson junctions are just in SPICE, so you just simulate them in these packaged programs, but not back then. Back then it was like,
hardcore.
Yeah.
So with your work experience under your belt, you arrived at Berkeley with all this knowledge of squids and Josephson junctions, charge density waves, and a little bit about solar cells. Who did you originally want to work for when you got to Berkeley?
Well, I wanted to work for John Clark, and but because I knew he was doing really nice work with squids, but he had just taken a couple of students, so his group was full. His group was full, yeah.
So who did you end up working with in the beginning?
I ended up working with Paul Richards, because Paul Richards was doing some work with he was doing SIS mixing. So you take these insulator superconducting elements, and you can use them as microwave mixers. And so that's kind of close to Josephson junctions and kind of interesting. And so he had a connection to the people at TRW. There's a strong connection between his group and the TRW group. And so I just kind of slipped into his group and started working on that project.
But then he also had you working on bolometers, right?
Yeah, that was also part of the project, because these SIS, Paul Richards at that time and still is very interested in detecting radiation, cosmic background wave radiation. So one way of doing it is in the microwave regime to use the SIS mixers, but in other frequency regimes to use this bolometer technology. So I was making SIS mixers and testing them, and also making bolometers with Andrew Lang. We were students together, so Andrew Lang taught me how to make his little spider web bolometers.
That became more in the realm of astrophysics, right? And it seems like astrophysics is something that you said you were interested in as far as reading about it in a magazine or hearing about it from colleagues, but it wasn't necessarily something that you wanted to commit your life to.
Yeah, because it turns out that, I was more interested in the devices. I'm more interested in solid-state physics, and so, the devices at the time were very interesting. There's interesting device physics with the SIS mixers, but it turns out that the really interesting physics was the astrophysics, what you actually would use it for, to look at the sky. And that's something that did not interest me so much. I mean, it interested me as something to read about in a magazine or to talk to my colleagues about, but not to actually do, 10 hours a day in a laboratory.
Right. So what role did Alex Zettel play at this point in your life?
I took a course from him when I was a graduate student. Well, I first saw what his students were doing because I was just hanging around with them, seeing what they were doing, looking at very novel materials, really interesting different materials, and like these different charge density wave materials was very interesting. And And then he taught a course on novel materials in physics, and he did a really nice job in this course, and it was really interesting to me. And so eventually I decided that that was where I wanted to go.
So when you joined Zettel's group, you were excited to work on charge density waves and to work on interesting questions, which, when answered, could explain the behavior of these materials. That was going to be your thesis research. Everybody was happy, and then something happened. What happened?
And then high temperature superconductors were discovered within months of when I joined, and so suddenly all the charge density wave ideas were tossed, and I became a high TC guy.
And that ended up being your thesis.
Yeah, and so I ended up working on high TC.
And was that fun and cool? The high
Yeah,
TC
it was
stuff?
great. It was a lot of fun because it was very new and exciting, and we were at the cutting edge, and things were developing very rapidly at that time, and we were doing a lot of different measurements. There were so many questions that were to explore. So it was a very exciting time. It was fun. I was very happy.
So you get out of graduate school, you're looking around, and you decide to do a postdoc. Why do a postdoc? Why was that right for you?
Well, it was just sort of the same answer as before. I didn't know what else to do. It was graduate school for me was very fun. I'm one of those people who really liked it. In fact, I think I would have just been happy to keep on, being a graduate student, but I think Alex said, "Oh, you should graduate, Mike." I said, "Okay." And then I didn't know exactly what I wanted to do, but I had realized, at least during graduate school, that I really liked doing research. So that was something I discovered from doing it, that it suited me, I liked it, it was fun. So I knew that I wanted to continue to do research. I didn't know where I would end up eventually or what I would do eventually, but I knew that I liked doing research. So.
And that's a realization that came to you after a long process of going to school and doing research day in and day out for a long time. I find it surprising when you get a 16-year-old that says, "I want to be a physics professor," because I don't think you can know that until you have put in the hours.
Yeah, I totally agree.
But we digress. So you were looking for a postdoc, but at that time the economy was not very good, was it?
Yeah, that was
Wasn't a great time.
1991. It was one of the downturns.
And you had been looking for postdoc positions and applying for everything, getting a few nibbles, but it wasn't looking so good. And then fate intervened. You got a phone call from Don Eigler. Now, we have a lot of different people in the crowd today, but Don did something that I think everybody here would recognize. What's one thing that Don is famous for?
He was the first person to controllably manipulate individual atoms. He used a scanning tunneling microscope to move atoms, and he spelled IBM in xenon atoms on a nickel surface. Yeah, nickel 100, I think.
Now, how did he get your number? Why did he call you?
Well, I just handed my resume to a recruiter, and so he just picked my resume out of a stack of resumes. It's totally random.
So when people say that never happens, it actually happens.
It happened to me, yeah. I had no idea really who he was. And I had no interest in scanning tunneling microscopy, to be honest, at that time.
And but you went to Almaden to interview.
Yeah, he invited me out, and I gave my high TC talk to him.
Did you feel like it was a natural fit for you to go down there and do a postdoc with Don Eigler? Did that make sense?
Well, I was measuring the anisotropic thermal conductivity of high TC crystals.
And he was doing ultra-high vacuum surface
He was doing
science and
ultra-high
STM.
vacuum surface, right.
And for you, ultra-high vacuum was 10 to the minus torr, right?
10 to the minus 6.
Yeah.
Yeah, it was about as low as I would go. But,
He said
yeah.
it would be funny.
Mikhail chuckled a little bit. I saw him smile. So no, it was very frightening for me because Don Eigler is a whole different technology, all this ultra high vacuum stuff, and very serious scanning tunneling microscopy. Don at that time was really, at the very frontier of that field.
Yeah, he's doing cutting edge.
Yeah, well,
stuff.
he remained there for many years, and so his group is still there, and so he So all the technology and the complexity of it was really something I'd never had experience with before, so it was pretty intimidating, and it was just a completely new direction, a new area.
It sounds pretty scary. I mean, what tipped the scales and made you decide to go do that?
Well, I think what did it was talking to Don, and Don, this idea of being able to move the atoms, Don had just recently demonstrated that that was possible, and so to me, that was so cool, and the idea of building things atom by atom, it was this new, no one else could do it. It was this new capability, this new technique, no one had explored it, and so the idea of being right there, sort of like Columbus discovering America, just that discovery aspect was so exciting that I wanted to try it out. I wanted to see if I could, what I wanted to do was build little wires and measure conductivity through little atomically fabricated circuits, something that I still want to do. But I think I'm going to do it now. I think I know how to do it now, 20 years later.
So if you were forced to, and I'm actually going to force you to, what would you list as the top 3 things that you learned during your postdoc?
Top 3 things that I learned, well, I mean, I learned that one of the most important things I learned is that I wanted to go into academia, which was, that I wanted to be a professor. That was when I kind of figured it out, when I was at IBM, because I hadn't really thought it through. But I think part of it was because at the time IBM was going through a downturn. IBM in the early 90s, it was a very difficult time for IBM, if anybody remembers, and so they were downsizing, and I knew that I really loved doing research and basic research, and so one of the things I realized is that I really wanted to do research in an academic environment at that time, and that was like number 1 important thing, because I feel doing basic research in this environment that we have here at UC Berkeley and at LBL, there's an appreciation for doing the very basic research, whereas doing it in an industrial environment, I felt that in order to be relevant in an industrial environment, to me, it seemed more important to do research which was very product oriented. Mm-hmm. And I wanted to do the more basic research, and so I felt that I wanted to do it in a different environment. So that was a big deal to make that decision and to understand that. Also, I learned the techniques of microscopy, which I still use today, mm-hmm. which is very important. That was number 2. And then number 3, I learned how to keep my mouth shut when I need to.
I'm still waiting for
that
personally.
That was a really important thing.
So you did your 2-year postdoc at IBM before becoming an assistant professor in the physics department at Boston University. In 1999, you moved your lab to UC Berkeley, at which time you joined the faculty as an associate professor. What prompted the move from Boston to Berkeley?
Well, there were several things. One thing was that my wife wanted to, that was one big thing. She really wanted, my late wife wanted to move back to Northern California, so that was a real impetus. But in addition, it was very appealing to come back to Berkeley, because Berkeley is such a great school. It has such strength in different departments, and so and also the fact that LBL is next to Berkeley, that was a huge incentive to come to Berkeley, because Berkeley is unique, as here we are, this connection between Berkeley and LBL, and so that was something that was very appealing to me because of all the collaborative possibilities and all the possibilities for research, which have really turned out to be true for me. So that attracted me, and that was a main reason for wanting to come here.
So you do a lot of different kinds of research in your group. You're part of Helios doing nanophotovoltaics. There's research on spin-based nanostructures, carbon nanostructures. But I'd like to start with molecular machines, because I think they're really cool. Let's start at the beginning. Biology is full of fully functioning nano machines. Can you give us an example of one of those?
Well, I mean, there's a lot of different molecular machines in our bodies. People like Jan Lippard and Carlos Bustamante study them in the biological context, like machines that make ATP and that make our muscles work. And I think all of these molecular machines involve, in some sense, the controlling conformational changes of molecules. And another place where this idea is really important is in our eyes. There's a molecule called retinol, and so when light hits this molecule, it changes its shape, its conformation, and that creates a chemical cascade that then causes a nerve to fire, and so we see.
And is this what motivated your research, or what motivated you? What got you interested to say, gee, I want to learn more about that?
No, that wasn't it. What got me interested is this idea of building synthetic machines. Well, I guess the biological machines are interesting and inspirational, but to me it's just so interesting, this idea of building machines at the molecular scale that might actually perform some useful task. That just seems like such a cool idea, to actually be able to not just move some atoms together and have them statically perform some function, but have them to be able to dynamically move around and perform some kind of function, walk around, build something, clean something up, move from one place to another. I like that idea, and that I think is very cool.
So there is a molecule called azobenzene, and you really like this molecule. Tell us why you like it and what you have learned from azobenzene.
Well, I was first introduced to this particular molecule by Jean Frichet. I was talking to Jean Frichet, and I said, Jean, I'm really interested in controlling how molecules move around on surfaces, and I want to make little machines, but I don't have any clue what molecule to use. And he said, why don't you do azobenzene? And it turns out that chemists have been studying this for many, many years, and it's a very interesting molecule that when you shine one frequency of light on it, it snaps into one conformation, but when you shine a different frequency of light, then it snaps into a different shape.
And so is that what's known as photoswitching?
Or photoisomerization, or you could call it photoswitching as well, because it's switching from one shape to another when it absorbs a photon.
Okay. So you want to observe single azobenzene molecules, and how do you do that? Are you using TEM, SEM, STM?
Well, what people had done before this work is the chemists had studied these molecules in solution, where you have millions of them floating around, and so chemists had figured out that these properties that the molecule switches around by shining light on it, but nobody had, you have to always be careful when you say nobody, but it hadn't been yet clearly demonstrated that when you put this molecule on a surface, that you could control it at the single molecule level and see what happens when it's sitting on a surface, which I think is very important, because many of the applications that you might envision involve having molecules and structures on surfaces. And so that was what interested me, was this idea of looking and controlling individual molecules and how they change shape and move around at a surface. And so,
but when you start putting things on surfaces, that it makes things a lot more complicated. What happened when you attempted to observe photoswitching for azobenzene absorbed to a gold surface, for example?
Well, it didn't work. We got these molecules, we put them on the surface, and we'd shine light on them day after day, and it just it did not work. So we tried a lot of different things, and we could not get these molecules to controllably switch. But then eventually we came up with this idea, a number of us, and the idea was to functionalize the molecule, to start lifting it up off of the surface, and then those molecules were made by Jean Frichet. And
so you made little legs.
Yeah, we added little legs to the molecule. As you can see over here, this guy right here, we added these little legs. Jean Frichet did that, and then the molecules started to switch when we shine light on them. We started to be able to control how they could switch on the surface.
Does the number of legs matter?
Yeah, it does. If we did 2 legs, it did not work. We had to put 4 legs.
Wow. Sounds like a long process.
Yeah, it was. But
and this is a slide of the
yeah, you can see these molecules here have switched. and we can zoom in on a single molecule. So this molecule has absorbed a photon and switched from here to here. Experimentally, this is what we saw, but then we can model it using theory with Steve and Louis, and we can see that the molecule is switching from this shape to that shape.
And is it reversible? Is this thing going back and forth?
It can be. It is reversible. We can switch it from one shape back to the other.
Is that important for
to me? That's important. Yeah, because I think it's very interesting to be able to have the molecule go from to have it cycle from one shape to another, having, because then you could reuse it in different ways. But to have it just go in one direction and stay put, I think is a lot less interesting and less applicable.
And is the rate at which it switches important?
Yeah, of course. I mean, these molecules in solution can switch very fast on picosecond time scale, but on the surface it's still a question, how fast is it switching?
So it seems like these molecules have little muscles, and when you shine light on them, they are changing shapes. They're pulling one direction, or they're twisting, or they're doing something. And you mentioned earlier about synthesizing molecules. So can you synthesize molecules to make them specifically functional, or to do exactly what you want them to do, to create a muscle that's going to do a specific thing?
That's one of the areas that we're really interested in studying, is exploring what is actually possible to do with these molecules. And so there are a lot of different molecules out there that have been discovered previously by chemists, but a lot of these molecules have not been explored yet by physicists or by people looking at the behavior of molecules on surfaces or in these nanoscale environments. So there's a lot that hasn't been done in this area, and a lot of molecules that have not been explored that have different functionality. So I think the answer is yes, there's a lot of different things that we can possibly do by using some of these different molecules or changing the structure of the molecules. And so we're exploring both of these avenues. We're taking the azobenzene and changing its structure to give it different properties, for example, to make it so that we can connect them together. And that's being done in collaboration with Jean Frichet. But we're also looking at other molecules as well that have where their electrical properties change as well as their mechanical properties when we switch them.
And you mentioned earlier making little tiny machines that do things. What would these little teeny machines do? What do you see for the future of this research?
Well, I mean, there's many possibilities, but one possibility would be to have these machines, for example, you could use them to build something. Like if you wanted to build something on a surface, or you wanted to, say, lay out some structure, these machines might walk on a surface and actually help to build tiny structures, or to disassemble structures, to actually walk on a surface. And for example, if you wanted to remove some contaminants from a surface, these machines might walk out and grab them as another example.
So we're going to move on because there's a lot of science to cover. Recent advances in synthesis have made it possible to fabricate whole new classes of carbon nanostructures. You have the buckyballs, carbon nanotubes, and single sheets of graphene. Let's talk about graphene. First off, carbon can take a lot of different forms, as we know. Two of these forms, graphite and diamond. What is the relationship between these two forms?
Well, those are the two forms of bulk carbon, graphite and diamond. And if you take a chunk of graphite, you can just look at it. You don't want to have it on your ring. It's not that pretty. It's black and chalky, and if you rub it on something, then you get black stuff, that rubs off. And that's why graphite is so useful in pencils. That's the pencil lead. So little bits of it rub off very easily. It's not so strong, whereas diamond, on the other hand, is transparent and very strong, the strongest material. So they're quite different, but yet they're both made out of carbon.
And now, just for the non-technical people in the audience, how is graphene different from graphite?
Well, so if you look at graphite over here, then the main difference why they behave so differently is that graphite is made of sheets of carbon. So the sheets are bonded the carbon in the sheets are strongly bonded, covalently bonded together in the two-dimensional sheets, and then the two-dimensional sheets are very loosely bonded, so you get this loose array of sheets. And so the three-dimensional stacking of these sheets, that's graphite, but each individual sheet is graphene.
Okay.
Now go to diamond, and the carbon is not bonded in two-dimensional sheets. It has a three-dimensional bonding arrangement. So so you get the atoms are covalently bonded in all three directions. So you get this very strong, rigid network in diamond, and that's why it's so strong.
And I had heard that graphene has the highest conductivity of any material at room temperature. Is that true, and is that important?
Yeah, it's really important because one of the beautiful things about graphene, I mean, the fact that we can isolate a single sheet of graphite, which is graphene, is a really significant advancement that occurred in the last, 4 years ago, in the group of Geim in Manchester, England. And so there's a lot of interest in using this single sheet of carbon as a substrate to create electrical devices or magnetic different devices. It has and so this single sheet of graphene is very strong because it has these directional bonds like diamond, but in the two dimensions. So it's strong like a membrane. But then in the third dimension, the orbitals bond. You get these things. The orbitals bond. It's not a rigid structural bond, but you get this very nice electrical connectivity from atom to atom. You get these things called pi bonds, and the electrons can jump from one atom to the other through these perpendicular bonds. So you get this extended electrical network, and the electrons can move very easily through it. And that's what you were saying. That gives it the very high conductivity at room temperature. And that's very significant because if we want to make electrical devices out of graphene, then the fact that electrons can move through it very easily is significant. That's people often refer to that as the mobility of the electron, and this high mobility makes it much more useful for different applications, such as high frequency applications where you want the electrons to move really fast and easily.
So does it conduct well in all four directions?
Well, because it's a two-dimensional sheet, the electrons can move very easily in the two dimensions.
Yeah.
And but one of the questions is, well, there's a lot of questions. I mean, like if I put electrical contacts onto the sheet, you want the electrons to also leave the sheet and go into the contacts. There's a lot of open questions about how we might actually make useful devices from graphene. But the basic properties are very promising, and that's why there's so much interest in this material.
And graphene is cool because you can cut it into different shapes as well. And the shapes matter. It matters if it's a triangle versus a circle or something like that. So, and you're going to explain this to me, because as it turns out, shape does matter. Because depending on the shape, you can change the quantum mechanical properties of the material. And so I actually don't really understand what I just said. So you could explain that a little bit.
Okay. Well, that's one of the things that I find so interesting about graphene, because it comes in this sheet, and so in principle you can just cut it up however you want. Unlike, for example, I mean, we used to study the buckyballs a lot. That doesn't mean we won't in the future, but buckyballs, they kind of come in one shape. You put them down, you get a nice little molecule that has one shape, and its properties are fixed. But graphene is a sheet that you could in principle cut up, and then you could cut like a piece of paper, and depending on the shape that you cut it up, you can give it completely different properties. And one way to think about that is by remembering that when electrons move through material, they are like waves. And so the waves of the electrons, so the electron, you can think of it having a wavelength. Like the electron, you know, like you can think of it as being, say, a wave of charge. Well, actually it's a probability wave, but there's a wave associated with the electron as it moves, and that wave has a wavelength to it, and you have to be able to fit those wavelengths into a material. And so if I change the size of the material by cutting it, like graphene, if I can cut it up into different widths, then you're changing the possible wavelengths that you can fit into that graphene. So if I shrink it down, that means that the wavelength has to be really small. and there's a relationship between the wavelength of an electron and its energy. So if I then have a fat piece of graphene, and I can put a very long wavelength electron in it, which is low energy, so I can change so it's this whole business about fitting the wavelengths. And so by changing the size, I'm packing different wavelengths into the graphene. So that's one way of quantum engineering the structures. There's other things too I didn't mention. There's also interesting things happening at the edges, because depending on how you terminate the edge of the graphene, you can get completely different properties for the electrons as they move on the edge, which is also very interesting.
So what is a possible dream device that you can imagine making from graphene?
Well, there's lots of different possible devices. We could, for example, you might want to make, let's say, a spintronic transistor. So you might want to. So maybe we could cut the graphene into a triangle shape so that it has a net magnetic moment, and then we could connect other pieces of graphene to it, and then we could pass electrical current, which might then the conductivity might then depend on the direction of the magnetic moment of a piece of graphene. So a spin-dependent switching transistor would be one very interesting device.
Is that what this is?
Well, this is kind of a piece of art that I cooked up to just give you a sense of the possibility of how such a circuit might actually look. But this is just meant to be schematic, to give you a sense that you could potentially cut up the graphene into different shapes, and the different widths, the different geometries will actually have different function. And for example, these could potentially be dopant atoms. So these could be donors and acceptors. So we could create a little p-n junction here, for example. So other possible applications would be solar cells, optical device. There are many optical devices that we could potentially make. Graphene has a very novel property that you can change. If you take 2 layers of graphene, you can change the band gap with an electric field. It just has a lot of interesting properties that have a lot of device potential. But that potential, it's still an open question whether we'll be able to make devices that will really, be useful in industry.
So there's a charge puddle story that I'd like you to tell. And it starts with a sheet of graphene. Now, earlier we saw a slide that was just a sheet of graphene, it's carbon, and it was completely uniform. We just saw these little bits of carbon. It's the same thing everywhere. And so one might assume that a sheet of graphene would be uniform. And that's where a group at Harvard started. They looked at a sheet of graphene. They were expecting to see one thing. They were expecting to see uniformity. But what they found were these charge puddles. And first of all, what is a charge puddle? And secondly, what did they think was causing these charge puddles?
Well, this was some really nice work done by Amir Yacobi's group. He's now at Harvard. I think the work was actually done in Israel. And this is their data. And using a microscope that was a scanning single electron transistor, they were able to measure puddles of charge on a sheet of graphene, regions where there are puddles of electrons, where you have a lot of charge, and then regions where there's a depletion of electrons, where we could say those are hole puddles. Mm-hmm. And so they saw this inhomogeneous regions of lots of charge here, less, more, these charge puddles, and that was a significant observation because as electrons move through graphene, they encounter these puddles of electrons and holes, and that changes the properties of graphene. So it was an important challenge to understand what's causing those puddles, what is their nature, how do they behave, and can we control them?
And one of the first theories was that these charge puddles were caused by the fact that the graphene wasn't completely flat, that it had waves in it.
Yeah, and so a lot of there have been. This was discovered just a couple years ago, and there were a lot of theories about what was causing those puddles of electrons. And the previous measurements were done with a spatial resolution of about 1,500 angstroms, 150 nanometers. So they weren't done with the spatial, the previous measurements weren't done with a spatial resolution that allows you to really correlate the charge density and homogeneities with atomic scale structure.
So how did you attack the problem when you saw it?
Well, so we felt that with our scanning tunneling microscope we might be able to investigate these charged puddles, and because the STM has such high spatial resolution, less than 1 nanometer, we were hoping to correlate the existence of these charged puddles with different small atomic scale structure of the graphene to see what is really causing the charged puddles.
And you actually proved that it did not correlate to any kind of curvature of the graphene. You found something different. Yeah,
so we sort of developed a new technique for using the STM to measure the charge density of the graphene. And because we have, so here is a plot of the charge density that we measured. So here you can see regions of enhanced charge density, regions of depleted charge density. So we were able to measure these puddles, these charged puddles, but with now a sub-nanometer spatial resolution, so we could see what the real length scale is down at the 20 nanometer level. And at the same time, we were able to measure the topography of the graphene with the spatial resolution of the STM, which is very high at the single nanometer level. And so that now allowed us to correlate these charge density puddles with the actual topography of the graphene. And so one of the first things we wanted to see was whether these puddles were correlated with the curvature of the graphene, because there were many theories where people said that if the graphene is curved on the surface, if it's sitting on a bumpy surface, then when the graphene is curved, that will make the electrons want to move away from certain regions or accumulate at other regions. So it was a very natural theory, and so we wanted to test that theory by seeing if the charge density patterns correlated with the curvature of the graphene. And so we did that, but when we look at these images, we saw no correlation there. So these results we felt were strong evidence against those theories.
And what did you eventually discover? What was causing these puddles?
So, well, at first we were pretty discouraged because we couldn't figure out what was causing them. We saw no correlation, but then eventually we were able to discover, eventually we did find these very small defects in the graphene sheet, which we believe are caused by molecules or charge traps trapped underneath the graphene. So we found these localized defects which correlated strongly, these localized defects here, which correlated strongly with the location of these regions of enhanced charge density. So the bottom line is we discovered these defects which were donating charge to the graphene, and so now we feel that we have very strong evidence that these charge inhomogeneities are caused by these localized defects, which we think are trapped molecules underneath the graphene sheet.
Okay. So the original assumption that the sheets would be uniform was wrong, and it sort of led people on a wild goose chase. So is this what is known in the science world as a good time? Is this fun for you when you see a problem like this?
Of course, because this is a great challenge. I mean, the idea is to figure out what's happening in these new systems, these new materials, and no material is ever perfect. And so we, as physicists and chemists and various scientists, one of our jobs is to figure out what is the behavior of real-world materials, which are not perfect. And so how do the materials behave when you put them in an imperfect environment, on a surface, or in the presence of contamination or defects, and how does that change the behavior? And in the case of graphene, it changed the behavior quite significantly. So it's important to understand how these materials behave in the real world, but at very small length scales as well.
Great. Well, we're running short on time, but I know that the nanophotovoltaic stuff is something that you're very much involved with. So I'm wondering if in 2 minutes you can tell us about these single molecule nanophotovoltaics. Why is it interesting? What have you done so far? And what do you plan for the future?
Okay.
No pressure.
All right. This work is part of a larger effort that is centered here at LBL, which is called the Helios Project, which involves what we're trying to do is to create artificial photosynthesis, something that could really impact the energy usage in the United States. As part of that problem, what we're trying to do is we're trying to figure out new ways to take light from the sun. We want that light to come in. We want it to hit a photovoltaic element, which is like a little solar cell, little solar battery, which will then separate the charge. So we get electrons in one direction, holes in the other. And then we want to use those electrons to drive catalytic reactions, which will then create fuel. For example, cracking water and getting hydrogen to come out. And so far, my own role in that project has been, so far, mainly focused on the photovoltaic element. In other words, how can we take photons from the sun and use them to separate charge like a solar battery? Now, most solar batteries that you see on people's roofs are macroscopic arrangements of, say, silicon, where you take two sheets of silicon, one that has a lot of electrons, and one that has that's rich in electrons, and the other sheet is deficient in electrons. You sandwich them together, and that is a solar cell. So what we wanted to do is to see if we could take that concept and shrink it down to the nanometer scale, to the size scale of molecules, so that we could have a solar cell the size of a molecule. And so in a collaboration with other members of Helios, such as Rachel Siegelman, whoever her name is up there, and Don Tilley, those guys, they are chemists who make these molecules. And so they made some molecules, and it's really quite neat. They made individual molecules that mimic this idea of having an electron-rich region on the molecule on one side and an electron-poor region of the molecule on the other side. And then these two regions are stuck together in a single molecule. So now we have a single molecule that behaves like a solar cell. And so so part of the work that we've done is to investigate these little molecular solar cells to see if they actually can work, to see how they actually how well they will function as solar cells. So we can use our STM to come down and look at them individually to test these ideas and to understand their behavior. And so part of the idea then is that we want to optimize. Now that we can come down and look at these molecular solar cells, we want to see if we can improve their performance. And part of the idea there is we want to create these devices we want to make devices that are cheap and easy to make. And these molecules are relatively cheap and easy to make. But we want to make them so that they also are efficient and perform well. And so that combination of having cheap and easy to make materials that perform well, that's something that hasn't happened yet. So we're trying to make that happen in our research. And so that's the short story.
Great. Well, the long story hopefully will come in the future.
Was that 2 minutes?
That was okay. Okay. It's all right.
Yeah, how was that?
So that was a chance for the audience to ask you any questions that they might have. So take it away.
I have a question about the graphene, and you're saying that there's other molecules trapped that are causing those defects in the flat graphene. Those are non-graphene, non-carbon molecules. So does that mean it's attached to a surface? Can you remove those molecules, or can you do it flat?
Yeah, so that's what, in fact, that's what people are doing is, one of the questions then is, well, if we, right now the graphene is sitting on top of silicon oxide, and that's quite useful for creating devices because we have the silicon oxide on top of a silicon wafer, and that's a very useful device geometry because we can electrically gate the graphene. But what some people are doing and what we're also doing is carving out the silicon oxide underneath the graphene so that it's suspended. And by doing that, we can start to test these ideas of what happens when we remove the stuff that's touching the graphene, and can we actually make the graphene perform better. It is an idea that we're testing, and in fact the graphene does perform better when you suspend it. And so that's work that's ongoing, is to see.
Stretched out like a spider web kind of thing?
Yeah, you can just have it suspended over a hole. In fact, there's a number of people here at Berkeley who are studying suspended graphene. Christian Kizilowski is one sitting right behind you. He's using the TEM. Is that Christian? Yeah. I don't want to embarrass myself. Eyes aren't so good. Yeah, but that's an important question. You know, what is influencing the graphene, and how can we control that and improve it?
This isn't really a science question, but you know, Paul and Steve Chu were talking about the urgency of solving these problems for America and all that. And I don't know if when they talk about urgency, they're saying we need more money or what. But when you work in your lab, and you guys all work 10 hours, 12 hours a day, I mean, does that urgency translate? And do you think like you can react to urgency, or do you think you just go in and do your thing every day and you'll get it when you get it?
I can see that Mikkel's perking up. I mean, there's okay. I mean, there's always some sense of urgency in what we do as scientists in the lab. I think you'll find that wherever you look, at least, you know, in good research institutions. So we're always feeling that sense of urgency. But I think this larger sense of urgency, one of the things that it does is it helps to, one of the things that it's doing, and I think that people like Steve Chu and Paul Vasados are trying to do, and others, is to start guiding us and pushing us to study certain problems instead of other problems, for example, and to start thinking more about some problems. For example, we could be studying the fact that we're studying photovoltaics, and that there's a lot more work going on in that is I mean, there's a lot of interesting physics, a lot of interesting science questions to be answered, but